All right, well, thanks for coming. This is a really good turnout, so I really appreciate it. I know you've got a lot of other talks, wonderful talks you could go to, so thank you very much for coming and listening to our talk. My name's David Brimley. I work for Hazelcast. This is Vladimir Schreiner. He works for Hazelcast, but we're not really here to talk too much about Hazelcast, even though it's a sponsored track. We're here to talk about streaming in the world of legacy applications. So an easy way to think about this, we're going to do this talk in two parts. So I'm David Brimley. I'm the man with the grey hair, so I'm therefore the legacy applications man. and Vladimir is the new, young, wonderful thing that we'll want to get our applications. So you want to go from me to Vladimir. That's the idea behind all of this. So why don't we kick off? So before we did this talk and we came up with the idea for it, there was, we was kind of, we had a few meetings. We were saying, well, what really is a legacy system? And I looked on Google and I looked at Twitter and I looked at a few other things. And people were defining legacy systems in lots of different ways. So there was a couple of things, and I've worked with legacy applications before, and I'm sure a lot of you have, and I assume that's why you're here. So the first thing is there's generally not very much documentation. The original devs have all long gone and left the organisation. There's zero tests for the application, and that's a pretty big deal. And this one's slightly unusual in that when you look at legacy applications as well, there's not really a concept of time around the data that they store. So you can't really ask questions of the data and of the system around any questions the business might give you or any of the business owners might give you about what's going on in the concept of time with this application. Can I go back in time and can I audit stuff? There was a couple of applications I've worked on in the past where, and I've worked in finance as a developer for most of my career prior to this in sort of trading systems and investment banks. And it was, about 20 years ago, you could pretty much write any application you wanted and you didn't really have to worry too much about auditors or people coming around and asking you about your system and how safe it was and could you provide any history to your system. And then these nasty auditors come along and said you need to audit your system. So we had all these relational databases and you somehow have to shoehorn some kind of audit table onto the end of everything and record all of the actions that go on in your system. And that's where this sort of time concept comes in, we think, with legacy applications. So, and how many people have read this book? Got quite a few hands, yeah. So it's quite if you haven't, it's quite an old book. I think it came out around about 2004. And it deals, and it's kind of language agnostic. There's a lot of Java examples in there, but there's some C++ and C# examples. But it deals with a nice abstract level of how you deal with legacy code and how you can start to, find ways in which you can, at a low risk, start changing your code base. Now, what we're here to talk about today is actually how you can transform the architecture of your legacy systems without actually having to change the code base of your legacy system. So if we go along, this is the other definition of a legacy system we came up with. And again, drawing on my own experience, the legacy system is obviously the money, sometimes or almost always the money maker in your organisation, right? It's the one system that it's legacy for a reason. It's making money, nobody's going to touch it, right? And therefore, it's way too scary to risk your career trying to change that legacy system, right? You'd have to be absolutely insane, of course, to want to work on the legacy system and start changing it. So it's usually built around, these are some assumptions. They're not, not true in 100% of the cases, but if you've got legacy systems from maybe that were written maybe 20 years ago, which is sort of when I was in my prime, it was generally a client-server system with a relational database, and you had some applications connecting to it, and that was really it. And this is what, if you opened up Visio on your Windows desktop 20 years ago and you drew out your Visio diagrams, you'd have a lot of application boxes. They might be different business applications, but they'd generally just be saving directly into some kind of relational database, and that was where all your data was stored. And so, then, and this has happened to me before, we had lots and lots of transactions flowing through this application. And this is where I first came across the terms, 20, 15 years ago of OLTP and OLAP, and I didn't really know what they were at the time, and people kept talking about them. So I thought I'd better try and find out what they meant. And just at a general high level, OLTP is your transaction processing systems, and OLAP is your analytics system, so where your businesses come to ask questions about the data and everything that's been going on. And generally we found that you couldn't really mix the two because of scalability and performance problems. So this is where you might have, if you've worked in legacy systems, where you would have heard the term of you've had your reporting database and your live transaction database. And then, of course, to do that, you need some kind of program that does ETL and takes data from one place to another. And based on all of that, I had a pretty good career for 10 years where I just wrote lots of programs that copied data from one database to another, and you was on call where the batch jobs are running every single night, and you get a call at 2 o'clock where a particular job failed because the database had run out of space, or someone had introduced new schema, or that was basically my life. I thought I was this wonderful computer programmer, but all I was doing was shuffling data from one place to another. So why are the reasons we want to try and get away from this sort of architecture? And we're here because we're talking about streaming. This is the streaming track. Just out of interest, how many people have been going to a lot of the streaming track presentations? So did you see some of the other presentations? So you kind of, and just one more question for my benefit. How many of you are already writing streaming architectures and applications? Okay, so maybe 50-50. And then obviously I'm hoping a lot of you are thinking about moving in that direction. So the first thing with these, relational databases and these legacy architectures is that they're, we're going back to this concept of time, and they're really rooted in the present. So there's this term on Wikipedia that you can look up. It's called the current database, and that's really a database, or not just relational, but any kind of data store that doesn't have a concept of time. It just stores the data that is valid now, so it doesn't keep a history of what's been changed in the database. Okay, and so we want to get away from that. And as I've said, it ignores the temporal value of the data. That's something that's immensely valuable to businesses now, is understanding the temporalness of data. And of course, if you start to build those types of things into your systems, you allow your business to start asking questions about what if, predictive analysis, going back in time, doing some kind of modelling and those kinds of things. And these types of things are quite important for machine learning, artificial intelligence, and just general business modelling. So we came across this new initiative around SQL and relational databases called SQL 2011, and I used a couple of these databases in the past. They really introduced the concept of time into the database, so they allow you to ask questions about rows in your data, about, give me all the data between this particular set of time, right, some time slices, and you can do queries about preceding a time and before a time. You can also do interesting things with referential integrity, so you can only insert into certain tables if something exists in another table based on a certain time that's occurred. And time in this case doesn't mean the clock time, it can mean other things as well, right? That came along, and unfortunately it came along at an exact time where I was working with some schemas in relational databases, where I was going through every single table in my database. This was when I got asked to add auditing into a particular system. I don't know if any of you have done this, but you've gone through your schema, and every single table you've added a start date, a start time, an end time, and a version. And I had to do that for every single table to give myself some sort of temporalness around data, and I could start to audit things. And of course, that becomes really, really hard to manage, because then you have to start managing that logic in the application as well. So that SQL 2011 came along just as I'd done that, but that would help you. It removes the application logic away from you. And we've already sort of touched on this, but we want to allow our business to answer questions now. So when the data arrives into our business or into our application, we want to answer that data immediately and give that information to the business or other systems as it arrives. And obviously that's why we like streaming for that. So we're going from this old idea of storing stuff in a database and then we process it afterwards, and we're going to, we're flipping on its head and we're saying we want to process and then store the information. And then lastly, we want to change because we want to go to this streaming architecture. The best way to get this and add on applications onto the side of a legacy system without having to change the code is some way of distributing events out of those legacy systems, right? We don't want to tinker around inside the legacy system too much, but we want to try and get some kind of messages out off of that island, you know, that barren island that is your legacy system. You want to send a message in a bottle off to these brand new things that you're building. If you'd have seen some of the earlier talks on streaming, some of them make this, statement that RDBMSs and other data stores, legacy data stores, are passive stores, right? There's this idea around them that you push. That's it. You can go. They're push over pull, and we want to go to another way. We want to do pull over push, right? And we've already spoken about this, but it's easy to integrate new systems onto the side of your legacy system if you start to adopt this. So I've mostly gone through that way too quickly for Vladimir. So I'm assuming you've all drunken the Kool-Aid. I'm not here to sell streaming systems to you. I've just come to set the scene. This is the legacy side of things. We're here now to try and talk to you about how you can take that legacy system and start to add new systems using that legacy systems database and data, right? Okay.
So what David basically introduced is impedance mismatch. So we have legacy applications, right? Legacy applications are mostly apps that do have an internal state. That state is usually changed by external actions, and as soon as the state changes, it's persisted to database, mostly relational. Those applications usually don't publish those changes. They just stored in a database. But what we would like to have is applications that inform us proactively about the changes in the business objects. So yeah, that's an impedance mismatch. And I'm also in the business for a while, so I experienced a similar thing maybe 15 years ago when people started to play a lot with object-oriented programming model, mostly with Java. But they still had relational databases, right? And objects form graphs, while tables form relations. Objects use specialization to build, more composite structures. Tables do not, it's different. With objects, it's quite obvious and frequent to use attribute reference, right, in another object. This is not something you can do in a relational database. So it was like two approaches, two concepts with a gap in between that created a market for ORM systems, things like Hibernate in Java, for example. I believe all of you met them in the past. To bridge the gap, which was not conceptually absolutely perfect, but the practical aspect of it just won. What we need right now is some Hibernate kind of thing that we can plug into our legacy application stacks to give us streams of changes so that we can build event-driven applications. The answer is CDC, change data capture. What that means, CDC is basically a technique how to convert a legacy stack to a source of streaming data, right? How this works is basically a plugin, let's call it like that. We will go to the technical details later, that you somehow connect to your database and it extracts changes. So as soon as there is an insert or update or delete or even a schema change in your legacy stack, the database publishes this information in a form of stream. So we are basically creating a new read-only API to a database. And as a client, you subscribe to this API, and the database is pushing and publishing changes in its internal state to you. How is this possible? The theory is that many databases are actually based on some kind of lock as part of its internals. So they contain a sequence of operations, and it's used internally for fault tolerance, for data replication, or for transaction coordination. So the idea here is, okay, let's take this log of database operations and let's make it public using some sort of API to which we can subscribe and get changes to the database. So without any change to the legacy application stack, we can basically integrate with it in a streaming way. How can this help? To explain it to you, I have to travel back in time. So when I was a teenager, I started playing ice hockey. Not sure how ice hockey is popular here in UK, but back home in Central Europe, it's a big deal. We started to play in a league, and what we needed was an application to manage that hockey league, right? So to record game schedules and rosters and to record scores and whatsoever. So we built it, and the application is running for nearly 20 years. It's a typical legacy stack. So it's based on MySQL with a web application, and over the years, it has like gigabytes of data. Most of the data or most of the operations are transactional. So something like insert a new row to the database when player is added to the roster, or list the scores, so simple select. But over time, we also added stats, and some stats tend to be pretty complicated. If you follow any sport games or whatsoever, you know that you can create very colorful stats. So the statistical queries on that MySQL instance took a few minutes to run. So what we did was basically running those analytical queries overnight. It wasn't a big deal since the data were recorded to the system after the game, so it was kind of batch oriented, so recomputing the stats once in a day was no big deal. However, a few years ago, we introduced an app for timekeepers. There is a guy or a lady at a ring, and every time something happens, so there is a goal, a goalie save, change in the timing, power play, or penalty killing, this is recorded in a real time. And when people realized that we are actually collecting the data in real time, they immediately started to expect that we will be updating all the stats in real time. And moreover, we will be sending updates to their clients, to their web clients in the real time, as they are following the games on their mobile phones and whatsoever. It wasn't really straightforward to model this type of use case just using the legacy stack. So I built a proof of concept, which I would like to demo to you, where I basically connected a CDC connector to my MySQL database, which extracts the changes, and I implemented a streaming query on top of the CDC data. So every time, okay, and this query computes computes and maintains top 10 scorers over ever recorded. So every time there is a new goal inserted to MySQL via the legacy application, the change information is kind of extracted by CDC. The stream processor recomputes the top 10 players, and if there is any change, it pushes the information back to the web application. I will show you code briefly. Before I do that, I will quickly introduce the tooling that I'm using for that. What I use for that is our stream processing thing called Hazelcast Jet. So the API I will be showing is API of Hazelcast Jet. And it's basically the open source stream processor that comes with connectors, including CDC. And it also contains an in-memory key value store. And we'll use all three components, therefore I'm mentioning that. Moreover, the nice thing about it that it's just a single Java binary with like clustering, and it doesn't have any other runtime dependencies apart from Java 8, which is a big deal. I used to be a Java programmer before I became part of the product team, and just having a simpler infrastructure was always a big deal for me. So yeah, that's the tooling we're gonna use. So when I show it in this diagram, this part will be running in our Jet cluster, right? So this will be the component I will be mostly focused on. So let me switch to IDE and show you the demo. There are actually three components that I will use. Okay, so this first JVM I'm gonna start is just an empty Jet cluster, right? It just starts, right now it's doing nothing. More interesting thing is this streaming job. So yeah, this is the API that I'm using to kind of define the streaming job. And if you are Java programmers and if you work with Java util stream, this is somehow similar. So it's a sequence of operations that define the step in the computational pipeline. And as you can see, the first step in the pipeline is actually configuring the CDC adapter to read from CDC. I'm going to start it, and then I'm going to explain how it actually works under the hood. So right now, this got submitted to the cluster, or it was just one JVM, but it got submitted to the stream processing engine. It connected to my MySQL database, and it started processing. The last thing I need is the client. This is just a simple Java client that, again, connects to the cluster, and every time there is an update in top 5 scorers, it prints a result to the command line. In the real world, you would wrap this with some kind of WebSocket server to push the changes directly to the web client. So how this actually works under the hood. So let me first focus on the CDC part. Unlike SQL, there is no unified way how to do this CDC, this change data capture, right? Various databases use various techniques and offer various APIs. With some databases, they have an API to directly read this transaction log. Some databases allow you to participate in their replication protocol. So you, as a guy doing the CDC, basically pretend that you are another member in their cluster who is interested in all the changes. Some databases have high-level streaming APIs, so that's an easy job. Therefore, there are many tools, many CDC API provided by many vendors. Most of them are proprietary. One of those that is open source and pretty good is called Debezium. We decided to use Debezium. Debezium is a set of connectors that you can plug into your Kafka infrastructure. So just by default, if you take vanilla Debezium, you need complete Kafka cluster, you plug it in, and it continuously reads data and publishes the changes in a Kafka topic. This requires complete Kafka infrastructure. So what we did was basically extracting just the connectors from Debezium and creating runtime for them in this Hazelcast Jet cluster. So still, by having just one Java library without any dependencies, you can do the CDC completely. How that actually works, this is, by the way, the configuration of my MySQL. I just wanted to illustrate that it's pretty straightforward, right? No need to do big changes. How this actually works, when the CDC connector connects to MySQL for the first time, it reads a snapshot of the database tables you are interested in. So it opens a repeatable read transaction and reads a snapshot of the table, and then it jumps to this transaction log and follows the changes. Right? Therefore, when I started the job, you saw a lot of records, a lot of updates, because that was actually reading the history of all goals recorded in my database. Okay, this brings some pros and cons, right? The biggest benefit of CDC clearly is that it's simple to deploy. You are just reusing your existing infrastructure. But there are some cons as well. Of course, it adds some load to your database. The database, for example, in this case, MySQL, must do more intensive transaction and operational logging. Every row that's recorded in this transaction log must contain all the information about the previous version, new version, and so on. It's not massive, but it adds some load to the database. And also, this operational log in the database, this transactional log, is usually pretty short. It contains just a few days of data. So you can't easily replay the complete history of all the changes that happen to your database, right? So if your use case is, for example, about detecting patterns, I don't know how many times each goal was changed or updated before I actually connected to it using my CDC connector. I will just see the changes started from now. So those are some cons. But even though I think this is a nice extension. Okay, So right now we have this streaming job, and I would like to add one more piece to the picture, which is cache. So let me jump back to the code. All right, so as part of this processing, one thing that I have to do is a lookup. So I'm receiving goals from the database, but I have to go through one mapping table to actually understand which player scored the goal. And this would be pretty heavy operation to do for every update, to do a lookup against the database that would massively slow down the whole computation. So what I actually did was using this key value store, this cache that's coming with this jet, and as a part of cluster startup, I actually eagerly download the lookup tables and keep them in cluster cache. And they are configured as read-through. So, okay, the tables, the lookup tables are usually not that big. It's, I don't know, tens of thousands of records. So I can do this as part of the cluster startup. And they are configured using this read-through behavior. So if some value is missing in the cache, it automatically goes to the MySQL to fetch the missing value. So that's pretty smart, and I'm mentioning this because doing join-like behavior is pretty frequent, like analytical operation. So having actually a cache as part of your streaming solution might help significantly. Okay. One more thing I would like to mention is that this architecture is event-driven end-to-end, right? As soon as user writes something, or my legacy app writes something to the database, the change is immediately written or extracted by the CDC. The stream processor is like data-driven by definition. It updates the stats, and if there is a change, it immediately pushes the change to the client. And to show you how this works, okay, so this is the log of operations from the client, and this is the legacy app, and this is how the timekeeper's application look like. And if I add a goal, we will see that it immediately shows in an application log. So this way, you can use your legacy application and make it event-driven, which I think is pretty big deal because this is quite frequent requirement when building modern applications. All right, so to wrap this up, I think that when you combine CDC with stream processing or with streaming and with cache, you basically get a pretty nice tooling to build materialized views that are offloaded from the database. Right? Materialized view is eventually consistent view on the data that's somehow optimized or organized for specific workloads. And the databases, they do have materialized views for a while. So what's the reason for actually offloading materialized views out of the DBs? So the first thing, or first reason that I see is that there is actually no perfect database to handle all different types of workloads. For example, with this demo, what I wanted was denormalized data, right? Relational databases are kind of built to have relations, not to store denormalized data, although you can use them like that. We also didn't need like durability. What we wanted was just the in-memory performance. And we wanted also the event-driven behavior, which is not something where relational databases are particularly good at, right? At the same time, again, relational databases aren't great for OLAP processing, like analytical processing. You can do like heavy analytical queries in relational DB, but it won't be perfectly performant. It's just about trade-offs and fine-tuning. So with materialized views offloaded from the DB, you can actually build kind of different database optimized for the specific workload to get the best of both worlds. Second reason is modularization and microservices. What I mean by that? The trend with microservices is that each microservice is self-contained, that it also contains and maintains the data and the infrastructure that it needs for its operations. So with the CDC approach, what you can do is simply watch the changes on the database, take the data, and store it in your microservice. The CDC makes sure that the data are always up to date. And then your microservice is kind of fully self-contained. The failures are isolated, right? If the main database, if the master database fails, your microservice still has all the data it needs for its operation. So that's quite a big deal. So yeah, in this case, it might mean that apart from the stat service, you can, for example, add another service which computes or predicts results based on the machine learning algorithm. Or you can have another service that takes all the data from MySQL, all the changes, and archives them for offline analytics or for model retraining, which is quite frequent nowadays. Okay, and the third reason I see for offloading materialized views from relational DBs, surprise, surprise, it's scaling. What I mean by that? Again, legacy databases usually host many types of workloads. They usually provide many types of functionalities, and scaling them simply means scaling many moving parts. It tends to be expensive. It tends to be a tough job. Whilst if you offload just the stream processing part, just a specific analytical job, you can use more lightweight infrastructure for that, so the whole job of scaling it will be technically cheaper. It goes hand in hand with this microservice approach, right? What I mean by that, for example, if I go back to this application that I use, right now the job is running just on one JVM, but what I can easily do is start another cluster instance. It will take a while. The nodes will discover each other, and they will basically balance the load between two machines. And that's it. That's all I need to do. It's pretty straightforward. Compare this with scaling your legacy relational database, right? So that's pretty much a big deal. How this works under the hood, basically the computation of the stats is split on the player ID. So half of the players are computed by one node, and the other half is computed by the other node. So I'll scale the computation this way. Moreover, the data are also replicated, right? So the solution is fault tolerant. So right now the computation is running. I can, for example, add another goal. So we are still seeing the correct updates, and both the cache data and the internal state of the streaming job are stored in the cluster in multiple replicas. So the infrastructure makes sure that the computation and the stored data are actually fault tolerant. So even if I lose one node from my cluster, the computation can easily survive, and the numbers stay correct. So adding another goal, you can see that it just increased, right? That the change in the cluster topology didn't actually affect the correctness of the computation. And the point really here is that doing this with a legacy database would be far more heavyweight job. That's what I wanted to point out. All right, let's come to the conclusions. So what are the recommendations or the conclusions here? So even if you are working on the legacy enterprise architectures, experiment with CDC. It's very straightforward and I would say lightweight way how to integrate with legacy applications. You will just slightly change the configuration of the database. It's usually not very invasive, since extracting a log of changes, it's a simple operation. There is no processing involved, right? Sometimes you just pretend that you are another member in the cluster of your legacy database. With this, one very specific and useful use case is actually using it together with stream processing to offload analytical workloads to create materialized views out of the DB. And this way, you can really create nice event-driven applications. And if you are in Java world, consider Hazelcast Jet, which is a nice open source library to do the job. All right, if you have any questions, we are happy to answer them. Yeah.
Thank you for the talk.
Thank you very much.
First of all, two questions. Hi. So thanks for the talk. It was very interesting. First of all, can we find in GitHub the coding samples or somewhere else?
You know what? I will make sure that the slides, including the links to the code samples, will be published after the talk.
Excellent. Yeah. And the second question about the deployment. Can you say a few words about how is the Hazelcast Jet deployed?
It's really just a Java library, right? So there are two modes how you can deploy them, or three, so to speak. Simplest way of running Hazelcast is just declaring it as a dependency in your Java application, and that's it. Then, whenever you want, you start a new Hazelcast instance, new Hazelcast cluster member, just in your JVM. So you can use this for kind of building embedded or OEM applications. Second mode is that you start it from a command line as a standalone cluster. And when you start multiple Hazelcast members on the same network, they form a cluster, they discover each self and form a cluster. Again, there are some possible configurations, but out of the box it's just work, they form a cluster. And of course the most modern solution is use the provided Kubernetes Helm chart or Docker images and just deploy it on your Kubernetes and managed Kubernetes environment. David, is there something you would like to add?
No, that covers it pretty much. I mean, there's Jet, which is part of the Hazelcast project, and there's also the INDG, which is the caching layer. So they're both open source, they're both Apache 2 licensed projects. They're on GitHub, so you can go to github/Hazelcast and you'll see all of the stuff there. And then there's hazelcast.org, and then jethazelcast.org as well. That pretty much covers it. Also, as well, we've got we've started to you know, Hazelcast itself is a commercial open source company, right? So we offer an open source, and we offer commercial, we offer support, and then we offer an enterprise. There's an enterprise version of the software as well. But pretty much everything you've seen here today, you'll be able to do, well, everything you've seen here today, you can do, and with all of the open source software. And we're also launching a cloud service as well. So if you think it's going to be something similar to, you know, MongoDB Atlas or something like that, where you just tell us some simple questions about what you want, and we go off and we manage the whole cluster for you. But you can just as well do it yourself on premise by downloading the software and just starting the processes up and forming clusters.
Did that answer the question?
Yes, thank you.
Yeah. Just one other thing to point out, sorry. Not so much for Jet, but for the INDG side as well, is polyglot. So although the cluster itself is made from Java processes, you can use all of the APIs for the cluster from you know, many different languages.
Yeah. Is there a way to produce fine-grained business events out of this CDC capture?
Usually not. Usually CDC is really just publishing changes on the table level. So what would you do then is, again, attaching a stream processor that somehow combines the table events to a business objects. The computation can be stateful, right? So you can, for example, I don't know, program stream processor to, as soon as it gets card opening event and card closing event, which is like a database appends together, then it publishes business events about card being completed, something like that. So you need to combine a CDC with a logic in a stream processor. CDCs themselves are usually kind of dumb. They just extract changes. This is what they do. Yes?
Yeah, I have a question about the I have a question about the change data capture. How invasive is it, and how you say well it takes a bit of extra load from your database, but have you any stats on that?
I unfortunately do not. So it's mostly guessing, but basing on the demos that we have done, it's not significant performance load. It's like a small few percent that it takes. But sorry, I don't have great numbers, so I don't have to. Just don't want to.
Thanks.
Yeah.
Hi, thank you very much for the speech. My question is, what databases do you work with?
That's a great question. Thank you very much. So the open source connectors right now cover MySQL, Postgres, MongoDB, and Microsoft SQL. Those are open source. There is incubating connector for Oracle, which is available just for experimentation right now.
Thank you so much for the talk. I have a couple small questions. Do you also notice some problems with Debezium? Is it all working perfectly fine? And the second thing, like you mentioned, yeah, the microservices still work fine, but I can imagine that if you're having a team responsible for the database and another team for the application, if there are some schema changes, like how do you deal with schema changes, for example?
Thank you for the question, because there is actually one answer for both. I would say that Debezium works just fine. It goes more to the architectural level and how you think about maintaining applications that run continuously in a long time. And schema changes is a major concern. So usually as part of the CDC, you don't get just changes in the tables, but also changes in the schema. And it's completely ordered. So for example, with MySQL, it's in the form of JSON messages, where the JSON message contains name of the table, type of operation, so whether it was create, update, or a schema change, and an old value and a new value. And it's JSON with a well-known structure, right? So based on that, you have to somehow adjust your application logic to be backwards compatible, so to speak. So this thing, it's not solved on the infrastructure level as of now. It's kind of delegated to the users to deal with that.
I mean, you could use JSON. JSON would be a nice way of passing stuff around, obviously, with microservices, but we do see people starting to use Avro as well quite a lot for this, so that, you know, if you use generic records in Avro, when you're processing and serializing, if you're going down the serialized object route, then Avro and generic records and passing schemas around and defensively coding your microservices so that it can handle different versions. So when you're drawing stuff out of this generic serialized object, you can ask if, you know, a certain field actually exists, right? And then just carry on processing if it doesn't. But that's the serialized object way, but JSON is the other way of going.
Yeah, right now it's an application level concern to deal with schema changes. You are informed, you get JSON message, but if your application, for example, uses some field that was removed by that schema change, then your application must be able to react on that. For example, stop consuming the changes so that you can deploy a new version of the application that can deal with that. I would say it's somehow similar. In the past, what I also kind of met was people using database tables for integration, right? It's still very present, so this is kind of similar thing. As soon as the table changes, all applications consuming it must be able to react. Yes?
What if some of the data is encrypted? Let's say you're using SQL Server, always encrypted columns.
To be honest, I don't know. I don't even know whether the transaction log contains the encrypted records, or they are encrypted on the database level, or who decrypts them? Clients or
SQL Server encrypts them.
Okay, so they are.
They're stored encrypted. In
I don't know.
So that should be something we should look up, right? For Debezium.
Thanks for a question.
Does Debezium store? You know, does Debezium decrypt the data, right? That's a job for you then, Vladimir.
Thank you. David is my superior, so thank you for putting in my backlog for tomorrow.
We don't have superiors. We're just colleagues.
Sorry, yeah, I was just going to add on to that. Maybe we should also check up on compression, because a lot of our data on the... To add to that, I think we should consider compression as well. A lot of the data that we have is compressed, and how would that handle?
Yeah, it's interesting. You would think that, you know, I guess it depends on at what point the compression takes place. It'd be quite nice if, as it came into the relational database, somehow the transaction log, you know, it's committed to the transaction
It is
log.
at the table level, so it would be stored with the schema changes, definitely for sure. I'm talking about Oracle here, and we know for sure it's stored with the schema definition. So if you look at the schema definition, it tells you it's been compressed. So,
and I suppose the kind of commit, you know, at the point that the transaction log is stamped to say that this is, you know, this is safe, would be after compression as well. So if you wanted to put it onto the stream, maybe you need to decompress potentially again.
correct, yes. So it is compressed at storage and decompressed at retrieval.
Yeah. It would make sense maybe if you could pass some kind of information along the transaction log about the compression algorithm as well, so that you don't need to decompress at that point. You can decompress maybe further down the stream as well. That would be useful. I'm just thinking out loud now. That would kind of be useful. But these are good points, actually, so thank you. We're sort of getting some stuff. So, yes, compression and encryption, we should, yes, definitely look at that.
Just another question around transaction stitching. So obviously, sometimes you need to trigger event based on a number of transactions, right? And then not always one transaction is for the single event. So does your library support that? Do you have means to deal with it?
Exactly. Again, it's something that you do in this stream processor itself. It can contain stateful computation. So really, it can define its own triggering criteria. You can really see the stream processor as the PL/SQL combined with triggers extracted from the database and it runs outside, right? So it gets all the notifications about data changes, and it can do any stateful computation based on this data, right? So for example, if you observe some transactional changes, you can count them, you can aggregate them in the time window, and then, run an operation based on that, and export a business even based on that.
Yeah.
So do you store them in kind of runtime memory, or there are means for storing them, caching?
The database internally stores them on a disk. The operational log or the transaction log or bin log in MySQL is persisted on a disk. The CDC extracts them to our cluster, and we just process them on the fly, so we are not storing them. And if there is any state, for example, if you are counting the transactions or buffering the transactions for a while to reason about that, we use the replicated in-memory store. So it's in memory, but the replica of that state is stored in another member of the cluster to stay fault tolerant. And the theory is that if you get some failure, you either get a replica from another member of the cluster, or if the cluster fails completely, you replay the data from the database which persists them. Yes, one more question.
Yeah. Hi, thank you for your talk. So what happens if the CDC was to drop a message and then your previous value is not consistent with the value you've got in the cluster already? What would the implications be of that?
I believe the CDC makes sure that there is exactly one delivery between the database and the consumer. So there can't be change in ordering. I believe this is a guarantee that it provides.
Okay, thank you.
How is it compared to, for example, Kafka? Because Kafka gives you connectors as well and visibility. How would you compare this type with the Kafka apart from Zookeeper that is not present there and it presents in Kafka, but Kafka is planning to get rid of Zookeeper?
So how this compared to Kafka? Kafka's role is mostly to become a database, right? But instead of storing current values of data, Kafka stores a history of changes. And my point was that there is actually a minified version of Kafka running in each database, which is this transaction log storing the history of all database operations. And whilst deploying a Kafka infrastructure in the legacy environment might be a tough job, what you can do is instead of using Kafka, use just this transaction log in database with CDC that exports it, that provides an API to read that. That's what I would say. Yeah, but yeah.
It might be worth contrasting Kafka streams with Jet. So we're not, Hazelcast Jet isn't a Kafka, right?
It's more like if you know the architecture of Kafka, there is a component called Kafka Streams, which you can use as a stream processor. So the solution I presented is more comparable to this Kafka Streams stream processor.
Yeah. So Jet would be Kafka Streams, right? And the database transactional would be Kafka itself.
Yes. Okay, I see a stop sign from the organizers.
But if you do want to carry on talking to us, we're here on the third floor. We've got a booth there. Or please do talk to us. I'm David at hazelcast.com, so that's fairly easy to remember. And
I'm Vladimir at hazelcast.com.
So Vladimir and David at hazelcast.com.
Thank you very much for coming.
Thank you.